collaboration team and the physical oceanography sub-team. So Wilbert can comment on the post side, but I'll just give a brief introduction for those who are not yet familiar with the Glaciers and Sea Level Collaboration Team. So my name is Caitlin Florentine. I work at the U.S. Geological Survey. My pronouns are she and her. And I co-lead the team with Joe McGregor, who is with NASA, and he's also here. And our main sort of priorities currently under the current Arctic Research Plan, which as Meredith described is coming to its close, but currently our team is focused on coordinating and integrating observations to improve understanding of the processes controlling the mass balance of Arctic land ice, and also improving numerical models to enhance projection of ice loss from Arctic land ice and the consequent impacts on global sea level, and to better understand the predictability of these processes. So that's what our team is up to in a nutshell. And sort of our main function is to coordinate these semi-regular webinars. And so with that, I can hand it over to Wilbert and or Joe if you want to make any other comments about framing today's webinar.
Thank you, Caitlin. That was a great introduction. So I'll just hand it right off to Wilbert.
It looks like Wilbert might be having some issues connecting to audio. So I'm going to work with him on that.
Okay, sounds good. Well, I'm sure there will be another chance for Wilbert to make some framing comments on the motivation for today's meeting, but I think without further ado, we can hand it over to our first speaker, Kristen Schill.
Great, thank you. I will go ahead and share my screen. All right, I'm assuming everyone can see this. We're good to go.
Okay, great, I'll ignore you. But of course, I would never really ignore you, but I'll ignore you for these few minutes.
Can people see this?
Yep, we can see it. And just
Okay.
a reminder to go ahead and mute yourself if you're not intending to speak. Thanks.
Perfect, great. Well, thank you for inviting me to speak today. My name is Kristen Schill. I'm a research assistant professor at the University of Maine. And today I'm going to be talking about some of the work that I did during my postdoc with Dave Sutherland at the University of Oregon. In this project, the goal of it really was to start to understand the impact of icebergs and iceberg melts on the fjord. And in order to do that, we really needed to understand how quickly icebergs were melting, in addition to how quickly they were moving and the fjord environment itself. So the reason that we had this question, quick little background, these are Tidewater Glaciers. They drain the ice sheet, and the one that we were specifically looking at were in Greenland. And once this glacier enters the ocean environment, it discharges both mass in its liquid and its ice form. Without these glaciers present, normally the ocean is warm and salty, or warm and less salty at the surface and cold and more salty at depth. But with these Tidewater Glaciers introduced into the system, they actually inject this cold water, which should sink, but very fresh water, which should float. So just the presence of meltwater can actually disturb and will disturb the normal, I guess, function of the stratification of ocean water. So icebergs are even an extension of this. And so this was the fjord that we were working in. It was in southeast Greenland, Thermalik Fjord. And you can actually see our ship over here to the left to give you a little bit of an idea of scale of these icebergs that are coming off of the glaciers in this region. And one of the main, or I guess one of the prominent reasons why this area is so critical is it's changing very quickly, but it's also adjacent to these important regions in the ocean where overturning is happening. And since icebergs and freshwater have an impact on fjord circulation, we're also trying to understand what the impact of all this additional freshwater is going to be in the global ocean. So here's our study site in southeast Greenland. And going back to icebergs, how do icebergs fit into this story? Why do icebergs matter? simply for all the things that make them icebergs. They melt, they're in the water, and they move. When they melt, they impact circulation, but they also provide nutrients to a system, so they can actually generate their own ecosystems. Whenever they're in the water, when they move from land into the ocean, they're contributing to sea level rise. And also they move. So we've all heard of the Titanic. So they pose threats to shipping, any type of offshore installation. But when they move and they melt, they're acting as point sources for freshwater injection. And so that's really what we're going to be talking about today, is this melting component of them. In order to answer the large question of what is going on and how are these iceberg melt impacting the fjord, we first needed to figure out how to measure melt of these icebergs. And what we did was we just used regular iceberg behavior. So if we think about icebergs, in hydrostatic equilibrium, about 10% of that mass is going to be above water, about 90% of mass below. If we were to melt back to this blue line, all of this mass would be gone. And if that water line stayed constant, we would now have more than 10% mass above and less than 90% below. In order to get back to that 10-90 split, we're going to have lowering of that iceberg surface. So that's precisely what we did. We came up with a plan to deploy GPS units on top of icebergs in order to measure that surface lowering. We combine that surface lowering with estimates of surface volume, we could then start to get at the overall mass loss rate. If we combine it with even more information, such as the full iceberg geometry, we could get the melt rate because we would know surface area. And if we found this full iceberg geometry multiple times, we could actually start to difference these geometries and get the melt rate with depth. So those were the goals of our project. However, we had to be very selective in the types of icebergs that we instrumented because we needed to be able to recover these GPS units. And so we needed icebergs that probably wouldn't capsize during the duration of our project. They needed to be large enough for a helicopter to land on them or hover over them. Ideally, there would be a ridge that was present so we wouldn't inadvertently swamp or drown our iceberg units. But they also need to be accessible by ship. So while the deployment of the GPS was by helicopter, the measuring of the geometry was done based from the ship. So our ships actually needed to be able to make it to those icebergs. So we couldn't deploy GPS on icebergs that were too surrounded or too constricted. So this was our field work flow. So we first went out in helicopter, evaluated the iceberg, took photographs, deployed GPS when it looked good. Next, went out by ship. We calculated the 3D geometry, collected measurements. And within our 3 field seasons, we were able to successfully instrument 10 individual icebergs and conduct full geometry on 34 surveys on 22 different icebergs. And so for just the purpose of this talk, I'm only going to focus on 2 of the icebergs we surveyed in the first year, 2017. To give you an idea of what it is like when we're going out and deploying these GPSs, here's a video of us doing recon. So this iceberg is about 500 meters across. It's very large, but you can also see that it has its own surface features. So it has rivers, it has lakes on the surface, it has cracks where this iceberg can deteriorate. Also, you're about to see the ship in the background over there on the right side. So these icebergs are extraordinarily large, but as soon as we deem them more or less stable, or at least stable for the next 8 days, we'll go ahead and we'll land on them. I'll jump out of the helicopter. Dave Sutherland's on the other side of this rope, making sure that I'm safe and connected to the helicopter if anything were to happen. But we deploy our geodetic GPS as well as an expendable GPS unit. The expendable unit actually relays position so we can find these icebergs when we're in the ship and survey them. So it's a very quick procedure. It's about 30 seconds maximum on the iceberg. And what we'll do is we'll deploy 2 GPS units per iceberg so that we can also get measurements of tilt and rotation. So here's what our iceberg looks like after it's instrumented. So there are 2 GPS units, our ship in the background. And again, with these units, we have to be able to recover them. And so we always try to place them far enough away from the edges so that we don't inadvertently send them into the ocean. These GPSs measure X, Y, and Z. And again, the thing that we're really interested in is this Z component because it's going to give us this surface lowering. However, it measures the absolute height, meaning that Z is also measuring the influence of the tide or the differences between the ellipsoid and the geoid, and also variations in atmospheric pressure. So we need to be able to remove all of these variables before we can actually look at the surface lowering rate. Once we do that, we'll get plots that look something like this, or that look exactly like this. So these are our 2 icebergs from 2017. Each of the red and black dots represent one of the GPS units that's on each of the icebergs. And the top plot is iceberg B and the bottom is iceberg A. And so from here, we can get the surface lowering rates. For iceberg A, we actually see quite a difference in these 2. We were able to confirm through the scans that this actually was due to tipping of the iceberg. So these are just those things that we need to be able to work around, and why a single GPS unit can give us an idea, but not an exact measurement. So from here, now that we have our lowering rate, we just need the geometry, and then we can be able to calculate all those other variables that we're interested in. To do that, we go back on our ship. And so these are the 2 key locations on the ship where we are collecting information. So that first, the upper deck, this is drone. This is where we launch our drone from. And this is what we use to collect the surface DEM. So we send the drone out, we collect a whole slew of pictures, run those through structure for motion to get a 3D point cloud. Down here at the bottom, we use a multi-beam. This is about 2 meters underneath the boat, underneath the ship. Here's a diagram from the side, and we tilt it 15 degrees upwards. So historically, these have really been used to map the bathymetry. They've also been tilted towards mapping the terminus of a glacier. However, icebergs present some interesting challenges. Predominantly, icebergs and the boat are both moving. And so we have a significant problem with reference frame. And neither are moving with consistent velocities. Also, icebergs have very unique geometries, which also makes it hard to tell if the way that you are trying to correct for all of this movement actually is working or not. And so here's an example of what maybe our raw data will look like from the multi-beam. So here we're looking at our iceberg from above, almost as if it's a muffin and the top of the muffin has been cut off and we're looking at the wrapper of that muffin. And so we have our boat survey. Our boat is moving around and to the right, whereas our iceberg is moving to the left. And so even though those 2 parallel walls are actually the exact same wall, they're offset in location just because of iceberg movement. And so we correct for this in 2 different ways. The first way, we look at the GPS that's on the iceberg to look at that motion. And then the second way, their second method that we've developed uses actually GoPro on the boat itself, on the ship itself, to calculate velocities and differences in velocities. And so once we calculate this motion, we're able to reverse it back out and come up with our actual iceberg geometry. From there, we combine our multi-beam data with our surface structure from motion to get a full iceberg geometry that looks something like this. And so here are those geometries for our iceberg A and our iceberg B. We have our surface lowering rates calculated from GPS. We've now been able to calculate the surface volume from our drone imagery. And we have the full iceberg surface area that was calculated from combining our drone with our multi-beam. So from this, we can calculate a melt rate. However, there's quite a caveat with this. And the caveat is that calculating a melt rate in this way assumes that all of the mass that is lost has been lost through melt. And when we're out in these fjords and we see these icebergs, we can see that there's multiple different ways that an iceberg can lose mass, both through melting and through mechanical deterioration. And being able to partition these impacts on mass loss can actually help us to better predict the impact of icebergs on a fjord. So for example, if we were just looking at melt, this is a model that was created by Dustin Carroll, and this is just looking at melt on the bottom side of the iceberg. So this is the initial conditions, and with time, we see that freshwater not only is gaining in volume, but importantly, it's also remaining at depth. So the location with which meltwater comes off of the iceberg and enters its surrounding ocean is also impacting where that meltwater remains. And so this has a few different implications. The first is that if we had a melt-only scenario, which is a lot of what we're working on so far, we have our warm ocean water layer and our cool, fresh meltwater underneath. However, if we include this mechanical deterioration, so calving of pieces of ice, we now have additional icebergs at the surface, smaller pieces that have come off of the main iceberg. So all of their meltwater is being injected at the surface instead of at depth. So that warm ocean water may lower because that surface cold, fresh meltwater layer is thickening. This can have impacts certainly on the glacier. So if this is the type of water structure that's in contact with the glacier, you would have increased melting and susceptible to calving ice differently in a melt-only scenario versus a melt and mechanical deterioration scenario. So these are just some of the impacts or implications of why it's important to try to constrain this type of mass loss, whether it is entirely due to melt or we also have this mechanical deterioration. So some of the questions we have moving forward, we're currently working on, is can we more precisely measure iceberg deterioration? So I mentioned that we have 34 different iceberg surveys. 10 of those are actually repeat surveys. And so we have 10 different icebergs where we can difference time 1 to time 2. We also have 34 different iceberg surveys. And so we can start to get at this question of iceberg geometry and how it is impacted or changes with the size of the iceberg. Maybe we'll be able to establish a representative iceberg geometry that can be used in future modeling and remote sensing studies. And additionally, getting to this modeling question of when and where is meltwater injected. So that's a little bit of where we're headed next, but thank you for your time.
Thank you, Kristen. That was fantastic. I could look at your results and pictures all day. So I think we're going to transition right away to our second speaker. Wilbert is nodding his head. So Wilbert, if you want to inject something here, feel free. But I just want to tell everybody attending, you can feel free to queue up your questions in the chat.
No, this was great. I think you can hear me now. Yes, this was a wonderful presentation. Thank you, Kristen. I agree. So let's move on to Fiamma's presentation, and then we'll open it up for discussion afterwards.
Great talk, Kristen. Very nice. Okay, I'm gonna switch over. There we go. Can you see the screen? Perfect. Thank you. And thanks to Wilbert and Caitlin and all the other leads for these different IRPIC teams for inviting me. Now you saw all of Kristen's really cool result. We're going to change pace. I'm actually not really going to talk about science, but I want to talk about how we do science or how we can do science better as a community. And the focus is very parallel to some of the work that Kristen showed, and it's about processes happening at Greenland's margins. So the motivation for the group network, yes.
I just want to point out that it's not in presenter mode right now. So we're
Oh.
seeing the slides on the side.
That's sad because it is on my screen. Okay. Let's see if I can change that. Thank you. This is it better now?
Yes.
Okay. Nice. So it was on presenter mode in my screen. Okay, but it is now. So the motivation for this effort, which is called GRISO, which stands for Greenland Ice Sheet Ocean Network, it's a lot of the science that many people on this call are engaged in. And so the processes that are happening at Greenland's marine margins are key to understanding and projecting changes of the ice sheet, but also its impact as the ice sheet changes. It has an impact on the regional ocean, the marine ecosystem, and local communities. And you can think of these, it's useful to think of these as the ocean forcing the ice sheet. That usually means that the glaciologists are the ones really interested in the problem, and the oceanographers are providing input. You can think of it as the ice sheet forcing the ocean. This is where studies of, including Kristen's, of discharge of meltwater from Greenland or Greenland's impact on the ocean would go. So here's a picture of an AMOC and potential changes in the AMOC. Processes at Greenland's marine margin also have a big impact on ecosystems, and as well as the local Arctic communities that support them. And great. Okay, so the idea behind this network or this group is that understanding and projecting ice loss from Greenland and its impact on the ocean requires intentional, and I want to remark on intentional, inclusive, similarly important collaboration across disciplines, nations, and strategies for sharing of knowledge and data. What this group has been trying to do for many years now is it's really de-emphasize. We all do our individual science, we all do our group science, that's great, that's how we get promoted, hired, publish papers, but really some of the scale of the problems that we're dealing with require a pooling of resources, of expertise, and we can make sure that the science progresses a lot faster through this intentional and inclusive collaboration. So I'm going to go a little bit back in time because I do want to acknowledge that even though in the end I'm going to talk about its recently funded a new version of GRISO, GRISO has been operational with many people contributing to it for many years. It started as a US Cliver working group. And I think this conference that was held in 2013, where NSF and NASA program managers, as well as almost 100 other people participated from 11 countries, really spearheaded a lot of the collaborations in science that is happening now in this area. So this was in 2013. At this conference, we discussed what the scientific priorities should be to address. And at the time, the focus was very much on the ocean forcing the ice sheet. So how do we understand the dynamic changes happening at Greenland's glaciers and the contribution to sea level rise? The top priorities are somewhat still valid. They were identified there, they've evolved. An ocean observing system at Greenland's margins, process studies, megasite experiments, and bathymetry. Some of these have been addressed. I think the bathymetry, its identification at this workshop, as well as in other venues, really led to a number of efforts that have greatly improved our knowledge of the bathymetry and bedrock topography in Greenland. GRISO kept evolving. It was funded through the SEARCH program for a while. And this was another workshop we had. This one was focused on the Greenland Ice Sheet Ocean Observing System. Again, a large number of participants from 7 countries, including marine mammals experts, Greenland participants. And all of these workshops have reports. You can find them on the website. We also submitted a paper, an invited paper at the Oceanobs 2019 meeting. This is sort of where you make your pitch for observations in the ocean over the next decade. And again, this was a multidisciplinary effort. The last workshop we held was on the freshwater flux from Greenland. Again, that's a really nice report. And this was really aimed at bringing together the communities of ocean modelers, ice sheet modelers, oceanographers, glaciologists, studying the discharge of meltwater from the ice sheet into the ocean and how we can put it in models to ask the question of what is the impact of Greenland's changes on the local and large-scale ocean circulation. And just it's very difficult to measure the success of efforts that are aimed at building collaboration and facilitating interactions. But I just want to mention two. One is the bed machine free, which was led by Mathieu Merlingen. And I don't want to say that GRISO play a leading role, but GRISO did play a role in ensuring that the data from many of the PIs who go into the fjords and just collect bathymetry as a side product ended up in this product, which is Bed Machine V3, which all of you are using. And also I think I saw Jonathan on the Bamber on the list here, in really making the connection between some of the work that Mathieu was doing and some of the efforts, parallel efforts that were happening in Bristol. So that's one example. Another example, I saw Heiko on the call, ISMIP6. So GRISO and ISMIP6, which is the ice sheet modeling intercomparison effort, this new phase, have been having joint meetings, meaning we hold them in the same place and we interact over breaks and happy hours. And this led to this collaboration, which eventually produced the parametrization or ocean forcing for the ISMIP6 models that is now in the AR6, and some nice work by this entire community. And again, the people who are involved in these studies had to do all the work themselves, but I think the connection was seeded by GRISO activities. So this is the past of GRISO. You can see the workshops, some of the joint meetings, some of the motivation. And what I'd like to mention today is, how are we moving forward? And so we've been fortunate to have a new NSF-funded project. This is part of NSF's AxelNet program. And AxelNet, for those of you who are not familiar with it, is an NSF program aimed at fostering international collaboration. This is not about doing the science. There isn't science per se funding in this project, but it is about really building some of these bridges that enable the science to be done. And so I want to acknowledge the PIs and scientists participating in this effort. So Dave Sutherland, Twyla Moon, and Nguyen, Donald Slater, and James Holt. And again, the motivation and the principles are very similar to what GRISO has done in the past, and still valid. So the goal here is facilitate the interaction, both amongst individuals, but also groups, networks, and international networks in particular, and promote inclusive and open and collaborative practices in current and future scientists. And by future scientists, what I mean is there's a very strong sort of training, educational component in this project. So the new GRISO has several pieces that it's going to target. One is 3 working groups that are going to target the sort of free scientific questions or foci that I mentioned earlier. So the ocean forcing the ice sheet or the glaciers, the glacier forcing the ocean. And then the working group 3 is really the impact on marine ecosystems. And local communities. And obviously these are not distinct, but the idea is that these working group will move forward on some of the science questions relevant to these three categories. We also have funding for a series of summer schools that will hopefully take place in Greenland, COVID permitting, over the future years. These are really aimed at early careers. And again, the principle is one of across discipline, across nation, and also engagement with local scientists and local communities. We're going to hold a number of community workshops and also build on the work that's already been done to set up the ice ocean observing system in terms of defining what the protocols for data sharing, data processing, data collection should be. We motivated GRISO, by sort of reviewing all of the relevant networks or groups. By network, I mean a group of scientists or large projects that are operating, not always cognizant of other groups or networks work. And so we've clustered them here. You see a lot of acronyms. You don't have to recognize them all. The point is to show that there are networks that revolve around the ocean, networks that revolve around ice sheet questions. The glaciers, fjords is more in the central side here, and humans, including APEX, the Association for Polar Early Career Scientists. IARPIC is here, I ask. So, and Greenland scientific and entities, as well as governmental and non-governmental entities that are focused on local communities. So I'm going to stop here and take questions. I'm just going to say, if you're interested in participating, many of you have already filled the expression of interest or survey that we distributed on CryoList and a number of other list servers. But here's a link, and maybe I can put it in a chat in a minute. You can also find the link on the GRISO website, griso.ucsd.edu. Ways in which you can, the survey is meant to acquire information. We've had over 100, over 100 responses. We are about to email people back, but the idea is to define the community and the people interested. You can participate in a working group. This is one of the questions on the survey. If you're interested, we will reach back. You can participate in the establishment of the observing system. And lastly, there is a call for 2 postdocs, and here's the ad. And we are reaching out to the different networks or groups right now. One of the steps will be to give these networks or groups a possibility of summarizing what they're doing, what their plans are, and this will go up in the form of a brief presentation with a slide on the website. And so again, this is to create awareness of what is going on so that we do not have to duplicate efforts and we can really work together. Thank you. Stop sharing.
That's great. Thank you so much for the presentation, Fiamma, and everyone can again, put your questions in the chat. We have a couple of questions queued up. So I believe these questions are mostly for Kristen. We have one from Lori Padma. So if you want to unmute yourself, Lori, you can ask your question about mechanical deterioration and edge wasting of icebergs and connections to the tabular glaciers in Antarctica.
Yeah, this is Lori Padman. Great talk, Kristen. I was just wondering about, you started to mention the 2 ways of losing mass, the mechanical deterioration and the melting. And Ted Scambos has done a lot of work on what near surface melting does in order, by collapsing the aerial portion of the edge of the iceberg or the ice front. And that leads to stresses, then create another breakup of a small iceberg around the edge. So is that relevant at the scale of the smaller Greenland icebergs?
Yeah, great question. Thanks, Lori. It's certainly relevant on the larger ones. We have seen it on those ones, the ones that are like 700 to 500 meters in maximum width at the surface. Those seem to have enough mass that if you have just some wasting away at the water line, above will calve, and then we see a little bit later below will also calve. So you'll, on the really large icebergs, you'll keep those nice cliffs like you see on the tabular icebergs. Once they start decreasing in size, we actually see a lot more feet that extend beyond just the surface footprint. And so it seems to be less of a control on deterioration as the icebergs decrease. And when they decrease, they also overturn a lot. And so that might also be helping to mitigate those stresses.
I'll ask a brief follow-up question. So do you have a sense of the timescale that a buoyant foot would grow and create the edge wasting iceberg?
That's a great question. Our surveys were 8 days to 17 days. We did not see any form on that time frame. So it takes a little bit longer than that in order to form those. So I don't have any more information beyond that though.
Okay, thanks.
Yeah.
Thanks, Kristen. We next have a question from either Julian or Juliana Marson about melt plumes. So going back to melt instead of mechanical melting or mechanical mass loss. And there's also a comment about iceberg science collaboration. So go ahead and take the floor.
Hi, Kristen.
Hi.
So it was kind of more like a comment / question, but you mentioned that the melt coming from the iceberg enters like the lower depths of the ocean, but it is also possible that the melt will enter the ocean surface, and that's depending on the relative velocity between the melt plume and the background velocity of the ocean, correct? So you mentioned that you were going to further study this plume dispersion, which is super cool. And I just wanted to mention that I'm currently running a few simulations with NEMO, some with the melt plume entering at depth and others with the melt entering the surface. And then I will do a quick evaluation of how these different plumes can affect ocean physical properties and biogeochemical cycles as well. So yeah, so that's one thing. And the other comments that I did afterwards is just stay tuned this week still for an email from me. I'm planning to gather all the people interested in iceberg science, from the perspective of thermodynamic study of icebergs, or predicting trajectories for marine hazards, and for impacts on productivity, so how they carry iron to the ocean and everything. And this will, my goal is to include not only people working with Greenland, but also from Antarctica, because I think we can apply this iceberg science in both hemispheres. So hopefully this will get some traction and is in the same spirit as Grizzle, trying to not duplicate efforts. Yeah, so that's it.
Absolutely, yeah. So the model that I showed that Dustin Carroll put together, that was just looking at a basal tracer, and it was in the background of no stratification and an iceberg that was not moving. And so we're working to try to include all of those other parameters, but I'm sure as you have a lot of experience in. It's easier said than done. So this was just a very simple, just looking at the basal layer, not the side layer. But absolutely, where that iceberg melts within that water column, water is going to go in different places. Absolutely.
Yeah, just start with the spherical cowl, and then you keep adding the paws and the head afterwards.
Yeah.
You can complicate it a lot more. Yeah,
Exactly.
Thank you, Kristen.
Absolutely.
So speaking of added complexity, the last question in the queue in the chat is from Joe McGregor about the presence or absence of basal layers, or debris rather. So go ahead and voice your question, Joe.
Yeah, it's pretty much what I wrote in the chat. Did you notice any difference for any dirty icebergs? Were there any that were safe enough to survey?
Yeah, I read your question. So all of the icebergs that we instrumented were all those that had toppled. So we did not instrument any tabular icebergs, primarily because there aren't very many tabular icebergs in Sirmilik, and they tend to be very close to that transition point at Helheim Glacier, and so they're hard to access by boat. But they're also extraordinarily crevassed on the surface, and so there isn't a very nice ridge to land on. So that was one reason why we did not instrument any of the tabular ones, just not availability, access, or safety. There are some that we do see in this fjord that do have these really great sediment layers in them. We did not do any of those. So we tried to keep it somewhat simplistic, also because when we are calculating this surface lowering rate, we have to include some sort of density measurement for the ice itself. And so anytime you add in any type of sediment, that's going to alter that density. I mean, so do cracks and things like that. But with unknown how much density it would add, or how much of that loss was due to maybe rocks or boulders falling out of the ice, we just kept it simple for this run. We do have some beautiful pictures of them though.
Okay, great. Yeah, thanks. I'm thinking, I'm fairly ignorant of these topics, but I'm thinking that the ecosystem service of icebergs is probably quite dependent on those sediment layers or the basal ice, the more debris-rich basal ice. So yeah, hopefully a question worth exploring for the future. One follow-up that kind of surprised me. So you've got a lot of fieldwork experience, and what takes you 30 seconds outside a helicopter, takes probably 30 minutes for us desk jockeys. But I was surprised that you could actually deploy a GPS and get reliable results that quickly. And I've seen examples of videos. Tim Bartholomew has one of a setup of GPS on an ice sheet, and I've participated in some of these, and it could take a couple hours. So are there potential benefits to the measurements you'd like to make if the margin of safety was such that you could land for longer on the iceberg surface?
Yeah, so we actually deploy them and then leave them there for 8 to 17 days, and then we go back and we pick them up. So they are out for a period of time. There's certainly things that we could do to refine those measurements. If we could more safely, I would say, at least for me, it's not a matter of safely landing on the iceberg, while that's important, but to get better measurements to install more of these units. So they're expensive, they're geodetic. We had a limited number of units that we could deploy each year. If we were able to deploy 4 on an iceberg, we could really get at that tilt. And we could get at maybe non-uniform melting underneath the surface. In our last year, we actually stayed a little bit longer on the surface, about 15 minutes, and deployed an AP-RES system so that we could try to get that actual melt from underneath. We're still processing that data. As you might expect, it's very noisy. There's a lot of walls on an iceberg subsurface. But yeah, you can land for a little bit longer than 30 seconds and get away with it.
Thanks, Kristen. And while we're on the topic of a wish list, so data density certainly always there. And thank you for describing exactly what processes or problems could be constrained. And we have a question from Ken Mankoff for Fiamma about next direction. So Ken, you can unmute yourself if you have that ability to ask your question.
Yeah, I can unmute, but so the question was just, you know, the 2013 paper by Fiamma I found very helpful for sort of, you know, a wish list. And I guess this is also a little bit in the 2019 Frontiers paper sort of with the GRISO directions. But my question is, what is the one highest priority of a product that you think would be beneficial to the community?
Thanks, Ken. Well, some of the products you've been involved in are going to be really useful. Some of it is access to data and data synthesis that can serve multiple disciplines. But I think some of the other questions have to do with, you know, what do communities need now? It depends. So your question depends on who do you want to privilege. If we're interested in understanding the impact of Greenland meltwater on the large-scale ocean circulation, large-scale ocean models will not be resolving fjords anytime soon. We will need to parameterize or somehow prescribe the discharge. Even if you're using for future projections output from an ice sheet model, you will need to somehow take into account the transformation of the meltwater through all the complexity of processes such as those that Kristen described, ice that melts in a stratified ocean. How does it eventually make it out? And so I think the freshwater workshop in 2018 identified a series of new targets that depending on the community, whether it's the large-scale ocean modelers or whether it is communities interested, for example, in biogeochemical or biochemical tracers, fluxes, and so on. And that's what you care about for ecosystems. On the ice sheet side, you want, I think the ISMIP 6 effort that many people were involved with is a first, but very crude. We all acknowledged it. I think we talked about it at an earlier IRPIC meeting. It is a first step. There's a huge amount of learning that happens in it, but right now, still for ocean forcing ice sheet, our ability to do it ice sheet wide is very crude. And there's lots of improvements that can happen there. So this is from the modeling perspective. So again, it varies depending on audiences. A lot of these interests are overlapping. I think the big picture questions don't change and haven't changed since 2013, the workshop, the various synthesis articles, but the next step keeps changing. We've done some things, we can keep building on them.
Thank you, Fiamma. And we have a question from Thorsten Marcus along those lines of framing. So Thorsten, if you can unmute yourself and ask your question.
Yeah, I can gladly do this. Hi, Fiamma. I love the effort. It's really wonderful to see that, you know, that's moving on, and it's great. I was just wondering, you have these two working groups. One is oceans forcing glaciers, and one is glaciers forcing oceans. And I was just wondering why the separation, why isn't there, you know, like a certain focus at least on, you know, interactions of interdependencies, if you will.
Yeah, I think ultimately, if we talk from a modeling perspective, you know, the answer to your question is easy. Ideally, we want fully coupled ice sheets and ocean models. This is unlikely to happen on the sort of international scale for a lot of modeling centers for quite some time. There are many details that I think we still have to understand to do this properly. And so in the meantime, there's a need for the ice sheet modelers, ultimately it's melt rates, or as we did for ISMIP6, it was even more brutal. We prescribe retreat rates because many of the ice sheet models don't have the capability to represent calving yet. The next iteration will probably be models that can represent calving, but might still need melt rates from the ocean that are spatially and temporally variable. On the ocean side, I think the community is really interested in what is coming off of Greenland, where is it going? What is the subglacial discharge comes in? We can maybe have some idea from regional atmospheric models, but between where it enters the ocean and between where it enters at the head of a fjord and how it exits, there's a whole set of ocean-related dynamics that transforms it, which the ocean models will not be representing for a while. So they might need something different. But the idea of the working groups is not that they work in isolation, but that they hopefully will talk to each other. And I think that the biggest achievement is to get junior people involved, because some of these questions will take some time to answer, and sort of, yeah, the progress of multiple generations.
Yeah, thanks much. Makes perfect sense. Thanks. Appreciate it.
Well, we have about 5 minutes left before the top of the hour. This has been a really enriching discussion so far, but is there anybody who hasn't had a chance to ask a question who wants to either voice a question or make a comment?
So I do have a question for Fiamma, and that is, I mean, I was really impressed by this, by the GRISO initiative and all the collaboration building efforts. You showed that plot with all the acronyms, and IARPIC was there. So looks like you got a lot of ground covered already in terms of the collaboration. So do you have any thoughts on where how IARPIC can facilitate this effort?
Oh, that's a tough one, Wilbert. I mean, I think IARPIC has been great in bringing some of these communities together, also through these various activities. I haven't looked at the strategic plan or the new plan of IARPIC, although GRISO did contribute to the earlier one. But I think IARPIC is part of the efforts that are happening to bridge gaps. So I think, you know, maintaining communication and definitely getting some IARPIC people, which doesn't mean anything because you are all IARPIC people. So it's all one big community, but really just raising awareness of what is happening in multiple ways. I'm hoping will just get the science progressing faster. And I think IARPIC can do a lot to promote, and I know it's already doing it, collaboration, data sharing, and really interaction between different groups and different funding agencies in the US for sure.
Can you say a little bit about the international makeup of the GRISO group? I mean, IARPIC is in principle US, but we've been, at least the physical oceanography team, if I may speak for ourselves, we've been very active and engaging the European community also. And we're very happy with that engagement. So what can you say a little bit about the international makeup of the GRISO team?
I mean, all I can say is that, you know, as we form these teams, including the summer schools and the workshops, we are paying close attention to ensure that we have international representation. And this is really linking international efforts. There are many research efforts happening in and around Greenland. Some are US based, some are EU based. Denmark is obviously very active, and scientists in Greenland are very active. There are people in Japan working very actively. I think we can just try and reduce some of the walls in between these efforts by putting people together in workshops or working groups. So I think that's, again, GRESO it's just meant to facilitate, so we can, I think the most, we can provide a structure for the interaction through some of these efforts that we're doing, and we'll make sure that is international. That's definitely in this, in our mandate, in part also due to the kind of NSF funding we've received.
Great, thanks.
That brings us to the top of the hour, so I believe we will wrap it for the day out of respect for everybody's time. But thank you all for attending. Thank you to our speakers for two really nice, engaging talks. Like Meredith mentioned, this will be posted, so feel free to send the link to anybody who's interested who couldn't attend, and take care and keep up the good work.
Yeah, thank you, everybody. It's great.
Bye, everyone.
Bye, thank you.
Goodbye.
Bye, everyone.